My name is Emin Askerov, and this is a lecture about business and lithium-ion batteries. So the lecture is specifically about business, not about the technology of lithium-ion batteries, and about technology. There are a lot of resources out there which you can dig in. More engineerically inclined, but here I will only speak about how companies make money in this sphere, what is the value chain, what are the use cases, what are the markets, and how that's going to develop in future. I will touch briefly upon the technologies that exist and what lithium-ion batteries are, what types, and how you put them together, because that is necessary to understand the business behind that. But I will rely mostly on my experience in this business, which I was actively participating since 2018. And I shared this insight already in this lecture that I gave first time for High School of Economics in Moscow in April 2023. And now I'm re-recording this lecture in English specifically for New Energy Advancement Hub. And this lecture will be posted there, along with any notes that I will mention here. So, let's get started. So, the lecture plan, how we will go about it. I will first shortly tell about myself, my experience in these markets, and then we will go to the batteries use cases and the markets. Then we will focus on the manufacturing of lithium-ion batteries, and specifically manufacturing for mobility. As you will see, mobility and cars, trucks, buses are the biggest market for lithium-ion batteries now, and making the batteries for that is important business and is important to the applications of batteries later on, which we will find in stationary storage. And then we'll speak a little bit about the future of the business in batteries. So who am I? My name is Emin Askerov, as I said, and I have spent about 20 years in energy industry, from power generation to the grids distribution. And in 2015-18, I was business development director and CEO of Vetro and Redwind. These companies owned or co-owned by Rosatom, and they operate in wind energy and manufacturing. And from 2019 to 2022, I was the CEO of Renera, lithium-ion batteries manufacturing company, also owned by Rosatom. So, without further ado, let's get to the business. So, first, let's start with the use cases, why we need batteries. I think the first time I really encountered batteries in my life when we were planning to build wind farms. And the picture on the left is the wind turbine which we were manufacturing. So I try to use mostly my pictures here, my photos. Where I use difference, there will be a reference. So there, when we were planning to build a wind farm, we were approached and asked whether we plan to build batteries with that. Well, we didn't, because at that time the renewables penetration of Russian grid was insignificant, and the system operator said that, well, we don't really need that. So we thought, okay, we don't have the use case for that now. But what is the use case for the batteries then? That has enabled their growth. So when you speak about use cases, you usually try to find what problem specifically does this specific technology solve. And batteries, in the sense, well, they just store energy until needed. And that's their main function. The grid, most modern grids were designed without that assumption. They were based on the opposite assumption that you consume the energy the moment it is produced, or produce the moment it is consumed, vice versa. So there was no need for storage as such. And there's still in many energy systems, there's no need for storage. So, but the batteries actually do what they do is they store energy until needed. So because there was no need for storage, they were not produced in mass. Where we had them? We had them in our cars, is lead acid batteries to kickstart the engine. And then we had them in our phones, computers, and so on, where we actually needed that energy to be stored and to enable us, to enable this digital mobility that we enjoy now. Now, another use case for the batteries is to provide instantaneous power. And when you really need that kick in energy so that you move something big like, I don't know, crane in the seaport, where you need to load something and you need a lot of power now, you need to move very heavy things. Again, use cases are quite limited. So if the two first use cases are quite limited in scope, then the third use case actually drives the batteries. The third use case is to reduce emission of greenhouse gases, or GHGs. And we can see now, if I just, we will get to that in the mobility section. And this particular use case of reducing emissions is extremely important for the development of business of batteries now, but we will get to that a little bit later. First of all, let us see how the batteries demand developed over time. So today the batteries are growing fast, and you can see this in both graphs. They show the market growth of batteries, all batteries, lithium-ion, lead-acid batteries, any kind of batteries that there were, the chemical batteries, because there are also like mechanical batteries and so on, but we will focus on the chemical batteries here. So the chemical batteries growing, and growing fast. And if you, by chemistry, on the left-hand side, you see that they grew, let's zoom in a little bit. Yeah. It was mostly lead-acid batteries. And the lead-acid batteries, it's the batteries which is so-called SLI, the start, light, and ignition batteries, trucks, cars, whatever. They were the majority market until 2010. Actually, no, until like a couple of years ago. But then they were overtaken by lithium-ion batteries. And that was due to automotive industry. Automotive industry being the main driver here. And actually, funny enough, it was, sorry, let me adjust this. Yeah. And the automotive industry was also the main consumer of lead-acid batteries. You can see on the right-hand side, the SLI, the start, light, and ignition batteries. They comprise the majority of demand up until 2010, and then other cases become interesting when we start to have our portable devices. You see the portable part becomes a little bit, adds a little bit to the demand. But then after 2013, we start to have automotive demand for lithium-ion growing very fast. And that you see here on the right-hand side, this brown shaded columns. They show that automotive by 2020 was one of the biggest customers of lithium-ion batteries. And if you add e-bikes or other things like, I don't know, forklifts and so on, there you have it. And SLI together, you have automotive as the main customer of the battery industry. Not so much portable, because during our normal day-to-day life, we see batteries, we encounter batteries mostly in computers and mobile phones. Maybe some toys, our remote control and so on. But the bulk of demand is not that. The bulk of demand is moving things around, like cars. So, this is likely to remain the case in future. So on the right-hand side, the graph on the right-hand side, check this out. Mobility application, this is the graph by McKinsey for last year. Mobility applications were the majority, and they will be majority by 2030. With stationary storage, which we will speak about later, comprising a little bit, just a little bit here, and the consumer electronics, our favorite, really, really tiny slice. Now, markets, region-wise, will be concentrated. Half of that will be China, as it is now, and then it will be the other part will be split almost equally between Europe, United States, and other countries in the world. So this already gives you an idea where all those batteries come from at the moment, but you probably already knew that. So, as we now seen, the main market is for mobility. So to move cars around, to move trucks around, buses, whatever, forklifts. And because that is the biggest market, so we need to understand it a little bit more, what drives this electrification. So a little detour. So this is the first project that we did in our company. So we retrofitted the 10 electric go-karts from internal combustion to battery drive, and there we are. We had a race. This is the first race that we did, and these carts could go like to 90 kilometers per hour in a few seconds. And on the right-hand side, that's me in the red jacket talking to a pilot about his experience driving this electric go-kart. And what he said to me is that all these kids are like 10, 12 years old. And what he said to me, well, first it goes fast, go really fast, enormous acceleration. And second, is almost no noise. And that's on one hand. There's a plus. On the other hand, there's a minus, because he said, I cannot hear approaching a competitor from behind. And I cannot maneuver because of that. So I have to always be alert for other pilots who's trying to overtake him. So I would say there's also a third one. If you ever been to a go-karting place, I mean, the fumes, they're just nauseating. I mean, for me, it was a reason not to go to go-karting. I was there once in my life, and I never actually went again, and have no intention to, unless it would be electric go-karting, where I wouldn't have any of those smells. So that's the project we kicked off our lithium-ion business, and this is also the same for many other businesses. So the key thing here is the GHG reduction. The use case for the batteries in the car industry, it's not solving any particular problem apart from GHG. I mean, internal combustion engines work perfectly in solving our day-to-day problems. I mean, going to the market, to the mall, or taking our family to the airport or on vacation, or kids to school and back. So the internal combustion engine serves just fine. I mean, switching to electric will not give you any additional value. I mean, the use case is not there, except for the GHG reduction. So the transport today is the second biggest emitter, overtaking 8 billion ton annually. That, so let me just overtake it here. And that's important. That's important because that's where we can reduce emissions fast. As battery-driven vehicles become cheaper, more widespread, they can really solve that problem. And consumers around the world also see that that's the problem they want to solve. They are ready to buy the electric car, not only because not because it's some reason better than the ICE car, it's just because it's cleaner. Other benefits such as low maintenance, you don't have to pay for the fuel, yes, they exist, but they generally today are offset by the range anxiety, whether you find the charger or not. So today people buy this. The main driver is either financial, that this particular country has some tax deductibles or subsidies for that, or environmental. You buy that transport because you really care about the emissions that you make. Now, the emissions are really truly higher if you drive the ICE cars, and that there are holy wars going on the web whether electric cars are so really that clean as they claim to be. Well, they are. They actually are cleaner. And here's the comparison between the battery electric vehicles, the BEVs, and ICE, the internal combustion engines, in different countries, like say the biggest polluters, the United States and Europe. And that's the lifetime CO2 emissions, CO2 equivalent emissions, are dependent on the power mix that you have. The United States have a little bit more coal than Europe in the energy mix. So, and the driving habits, the cars themselves pollute differently in the United States than in Europe. And but even in the United States, you see that the ICE, the gasoline car, has the biggest life cycle emissions than battery electric vehicle under the current grid mix. Now, if a grid would be clean, I mean, nuclear, wind, solar, only hydro, only running on those, then this would be the battery electric vehicles would even have even less lifetime emissions than in the current conditions. And in the Europe, I mean, okay, the gasoline vehicles do emit less. Well, first of all, Europeans drive smaller cars. They have less engine volume and more fuel economy. So, of course, they have like twice less than US emissions over the lifetime. But still, the battery electric vehicles cut those in two. You could see here also the production emissions, the very dark, the navy blue color here. And this shows that to manufacture a battery electric vehicle actually produces more emission than manufacturing the gasoline car. And that's what everybody usually refers to. Oh, it's, so much resources you need to devote to this. Now, true, but it's always amuses me when people use that argument, because we're not buying electric cars, not building electric cars for them to sit outside. I mean, we're not using them as our cupboard or a piece of furniture. I mean, it's not a piece of art. Well, some are, but that's rare. We buy them to drive. And driving is what matters, as we can see clearly from this picture. The driving actually is where emissions are in any type of vehicle. So that's important, and it's important to keep in mind. And even if the grid is run on coal, even there's almost no grid that like this, like 100% coal nowadays, but you do get less emissions if you are driving a battery electric vehicle. Now, let me move a little bit aside as well here. Let's talk about how batteries are made and delve a bit into actually all this mining things, all the mining problem that the battery industry has. So to make a electric car, first you need to make a battery for electric car. You need to extract some resources, the raw materials, the lithium, the cobalt, the nickel, graphite, whatever. You need to process those materials. You cannot just, slot them into roll them into a battery or push them into cylindrical or prismatic plastic box and make it work. So no, you have to first process it, make it ready for chemical reactions. So you make this processing and refining for raw materials into precursors for battery materials. And only then you actually start to manufacture, again, not the battery, but a cell. A cell is where the chemical reaction, charging and discharging, takes place. That's where all the magic happens. So you need to manufacture the cell. And only after that you actually do the pack, which is the stacking of cells together and making actual batteries. And then you actually do the vehicle. Okay, of course the vehicle itself has its own value chain, but as you probably know, 1/3 of a battery electrical vehicle or more, the cost of that, 1/3 of cost is a battery or more. The rest is everything else. Your car body, your sound system, your steering, whatever. And then there is a final stage, the recycling and reuse of the materials, cathodes, anodes, plastics, whatever. So let's go a little bit deeper here. What is the battery? So the battery itself is not a single thing. It's composed of three things. First of all, it's the cells. The most familiar one, the cell we are all familiar with are the cylindrical cells here. The cylindrical cells, it's quite common. I mean, we see them in our remote control and old style cassette players and so on. Also, there are, I didn't put it here, they are like tablet cells, which, you put in the watches or some tiny devices. But these are so insignificant in market size, so we just leave them out. Now, cylindrical cells used in the vehicles like Tesla look like your Duracell cell in your remote control, except they're a bit bigger. You can see on the right-hand side, there's a picture from one of the plants I was manufacturing plants there, where they test the cylindrical cells, and you see that they are a bit bigger than the one you would normally encounter in your electronic shop. Now, the other type is the prismatic cell, which is usually a plastic or steel prism or aluminum prism, and then there's a pouch cell, which looks like a small shopping bag with two handles. And all of these types, they can come in different sizes. Like a small pouch cell, a big pouch cell, small prismatic, big prismatic, and cylindricals also have different sizes. Now, the cells are usually then connected together in modules. So the modules here on the right-hand side, you see there's a modules ready for balancing, to check the charges, and so the cells stacked into modules joined together, and later these modules are actually joined into pack where you actually have which pack actually goes into electric vehicles. So here you have photos of Tesla pack, and you have photos of packs for electric buses, and so on and so on. So the pack is actually the container which protects the modules. It has a battery management system which manages which cells are charged, which are discharged, how fast. There is also a cooling system to make sure that the batteries do not overheat. And then there is also, you can have some safety features there as well. So that's your 101 on battery cell and pack. And this is how you actually make it. So to make a cell is one of the most difficult industrial process in the whole battery industry. So you start first with making electrodes. this picture with this coils of electrodes. You make electrode first by mixing, so-called slurry. You mix, say, cathode, anode separately. You mix them. You have your nickel or your cobalt or your lithium, and you mix them together in specific time for specific proportions. Then you get a sort of paste. There's also a solvent actually there, and to keep them all together. So and then you get a paste. In the paste, you put on a foil. One for, and you put anode, another you put cathodes, and then you dry that out to take out all the solvent that there is, or most of it. Then you do the calendaring, which is actually just basically press all the electrodes, and then you slit them. Slit them to the specific width of the cells that you're going to produce later. And then you dry them finally, and then they're ready. They're ready to be assembled to cells. So first of all, you start cutting there. Here you see the picture of the cells coming out of a machine, already cut and ready. So you stack them, you put the contact here, the current collector, and then you enclose. The enclosing is just basically put it in whatever format you want, like in a cylinder, you roll them in a cylinder, or you put it in a prism or in a pouch. And then you fill. The filling is when you fill the electrode, in which is the conductive material allowing ions to pass from cathode to anode and back. And then, so this is basically your cell is ready, but it's not yet. You have the final stages of formation, final singing, agent, and final control. Now, this takes on the longest time. It can take up to several days for electrodes, for the cells to be charged, discharged, and charged again, checked, getting all the gases out, final drying, and this really takes a lot of time. This is one of the biggest bottlenecks in all the cell manufacturing process. And all of this manufacturing process is usually highly technological. It's usually, there are almost no people involved. It used to be done by hand a long time ago, but some of this process is done by hand, and you can still see it in laboratories when they do this pasting, coating, drying, countering all by hand, but because they just make tests cell. But on the mass scale, it's all automated. Now, because it's so complex, you need some scale for the batteries to become really cheap. So the lithium-ion cell costs usually drop sharply at around 2 gigawatt-hour scale per year. So 2 gigawatt-hour batteries, if you produce, that's about the minimum efficient scale you would need to have a low-cost battery. Yeah, here you can see on the left, on this axis, on the y-axis, you see the costs per dollars per kilowatt-hour, and they drop to around 100 for so-called NMC cell. You'll see what it is in a little bit later. For now, it just suffice to say that this is one of the most used cells in automotive industry, and you really need, if you really want to get the minimum efficient scale in big time, and if your line breaks down or there is some malfunction, and you want to keep on rolling, you need a bigger factory. So you need to go 8 gigawatt or more, and that's a huge thing. I mean, that's why we hear this word came into our vocabulary, the gigafactory. So you can see here, it takes about like $150 million to build 2 gigawatt of cell manufacturing. That's your minimum entry ticket into this business. But if you really want to compete and if you really want to get some meaningful market share, you have to go higher. And you would have to go to something like 10, 8 gigawatt. And the more you build and the more technology for the manufacturing of the battery gets advanced, the lower will be the costs per gigawatt. So you can see here the required investment in million US dollars per gigawatt in future is estimated at like 54 million US dollars per gigawatt. And from the quotes I see now, it's getting there. It's getting there fast. Of course, still your total capital expenditure, including your balance of plant, equipment, would be closer to $100 million, but it's going down. Now, if you want to go big and you want to go get efficient scale, this is what it says here, to reach minimum efficient scale, you would need like $820 million. So you're close to $1 billion to just, stay above the water. Now, here's the product process materials. This is really not important to us at this moment. This is from one of the scientific paper, Economics of Scale in battery and cell manufacturing. But the message here that the battery business is about scale. And you can see that from this picture, it's a big boys business. You see the factories are huge, like Tesla Panasonic factory, 76 gigawatt. That's their target volume in 2025. SK Innovation, new factory, 13 gigawatt hour in US. You see on average, I would say like 20, 30 gigawatt hour, that's the factories that companies are planning to build. And you see that most of them, who they are? Panasonic, LG Chem, CATL, and Tesla, and Samsung. That's the big companies that are running this business now. And there you see allocated mostly China, Korea, Japan, Europe, and United States. However, pack manufacturing, when you get your cells and you want to put them in some box, then so that you can put it in the car or in your vehicle or into something. Now that's much easier. You don't need millions to do that. Here are the pictures from 2 pack manufacturing facilities that I visited in Russia. And you see both of them, they're basically just a garage. You have some electrical equipment, some guys who know the way around electrical workshop, and there you have it. In the business plan I've done myself and seen, equipment for such a workshop would rarely cost more than $100,000. So that's easily set up and easily made, and a lot of startups in this space, but I would say that this is a highly competitive business. We have very low entry ticket, but a lot of competition. And one of the main things is that as we will see a little bit later, there are advances made now that will probably make this business redundant in a few years. But first, before we go to the forecasting, to the possibilities for the future of battery business, let's check out the stationary storage, because that was a lot of time there is on the news. If you are in the energy industry, see people talking about stationary storage, it's important, we need to have it, and so on and so forth. Well, is that true? Do you really need that? There's a picture of the first stationary storage we did for 300 kilowatt for an industrial customer. And, well, yeah, you do have some use cases for that. Here's an example. One of the first projects was done in our company, replaced a UPS system which was ran on the lead acid batteries. And you see, like the picture before, an operator maintains and checks the lead acid batteries, which is quite a hazard actually. You have acid there, you need to replace that, and there are fumes. It's dangerous and takes lots of space, as you can see. So we changed it to lithium-ion, and the same battery capacity fit instead of room in just 4 cupboards, as you see in the picture below. So we basically got the 3-year payback. We eliminate health safety risks. We had more space and longer service time, and it was fully automated. So it would already be quite efficient at some use cases to replace existing lead acid systems with lithium-ion if you really cared. But the thing is that in most of businesses, this kind of backup is so far down on the list of things that you need to do as a manager of a facility that you usually never bother to get around to that. Although there are some savings to be made. Now, the stationary storage market is quite insignificant. I mean, the ESS, so-called electricity energy storage systems here. So you have the total market, and you have EV buses, starlight ignition, portable devices, and then you have about 30 billion out of, like a third, for other applications, among which you have e-bikes, power tools, forklifts, other motives also. And then you have telecoms, UPS, ESS. This is your stationary storage market, which is small. And in that market, you usually run on lead acid batteries, not so much on lithium-ion. Lithium-ion does take slowly over that, but because of the niche and because it's, you don't, if you run a warehouse, what drives your forklifts is not, immediately on your agenda. So you get there eventually, especially when you realize that the batteries are so cheap that you can refurbish your lead acid forklift with a lithium-ion battery and be better off. So, but it still takes time. Now, the use cases for the stationary storage without the renewable energy in the grid, quite very few. You see there by the light orange, squares, it's black start, output optimization, backup power, and so-called peak shaving. So very few cases. Now, if you add renewables, a lot of renewables to your grid, then you start to have all sorts of other use cases, which are mainly interesting for people running a renewable power station or balancing the grid. Not so much for general users. So then you have a lot of use cases for batteries. But on the research I've seen, the renewable energy sources have to provide more than 30% of the energy of the grid for any of this to become at least marginally relevant. Until you don't, so while your renewable energy develops, you don't need to put a storage. You need to put this container near every wind farm, solar farm. However, in places like where you have that penetration, or it's growing fast, you will start to have that. Like China, last year they put in place the policy that, okay, you build a wind farm or build a solar farm, build a storage nearby. Same in Turkey. And so every market where you have a lot of your renewables, you will need these batteries for all kind of different use. Like for there are a lot of arbitrary opportunities. There are frequency regulation, load issues, shifting loads, because the electricity generated by renewables is not consumed the moment it's generated. So because, as you understand, the wind blows different times where you are not at work or at home, and sun shines also. You want to watch your TV in the evening when the sun goes down, but the power is not there. So simply the load shifting will be, and peak shaving will be one of the main uses here. But still there are lots of others. But first, to get there, you do need to have a lot of renewables on the grid. So the load shifting and emergency power surge are the main uses, and here on this basic graph you see that how the load of your home would look to a system operator with energy storage system and no energy storage system. So without energy storage system, in the night you would have almost no consumption, and in the evening your consumption would peak. Also there will be some peak in the morning. Now if you put in the battery, you even out your consumption profile to the grid. So you consuming more in the night but less in the evening, and generally that makes for a more stable grid. And for example, there's a top right picture here as an example of that. This is a energy storage system, a 35 kilowatt energy storage system installed in a village outside Moscow to help with balancing and to help with any interruptions, because they can sustain, this storage system could sustain the village for several hours if there is an accident or interruption on the grid, while the grid maintenance team fix that. So it's quite, I would say, the stationary storage systems will grow, as we've seen in the projection by McKinsey, but still they will grow only in the markets where there's huge renewables penetration, and then they will be following the increase in renewables. So what will happen in the batteries business in the near future? Well, let's see how the market would grow by the 2030. So McKinsey projects like a five-fold growth from 2022 to 2030, which is significant. I mean, it's quite enormous, I would even say. And the biggest growth it sees in active materials and cell production. Of course, mostly concentrated in China, then Europe, then US, but that analysis was before Inflation Reduction Act. And I would think that this could change a little bit, reshuffling from Europe to United States. Now, you see, the interesting thing here is recycle and reuse. So recycle and reuse is still small investments. Now, there's a good reason for that, and we will come back to it in a moment. But let's first come back to raw materials. There's all the time you hear it talk about there will be a materials crunch coming up, or it already happened with lithium price spiking last year. Well, it is true. If we assume that the market will grow 5 times, then the demand for the lithium, say for the lithium carbonate, by 2030 will grow so much, but the supply will be laid by half. It won't be able to catch up so fast. The reason is that it takes very little time to build a battery facility. On the right hand side you can see, let's go back. On the right hand side you can see a graph from International Energy Agency. It's how many years it takes you to build something. Say if you want to build a battery or cell manufacturing, it takes you like just short of 5 years. EV manufacturing, 2 or 3 years. Cathode anode manufacturing facility, also 3-4 years. But then, if you want to build a mine for nickel or lithium, takes you like 15 years. You need to find it, verify, get all the permissions, then develop the mine, and then start extraction. That's a long time. So 10, 15 years means that if they started now, they would come online 2035, 2037, 2040. So much later than the demand for materials will peak. Pardon. So where does this lead us? It leads to two things. First is looking for chemistries which do not require so much raw materials, or not so many rare raw materials, or not so many difficult to extract raw materials. And the second is to recycle the existing that we have. So let's take them one by one. First, the chemistry. Now, here we get a little bit technical, but bear with me. So chemistry, there's no single lithium-ion battery. There are different chemistries of lithium-ion batteries. All of them have one thing in common: they have lithium in them. So, but there are other components in their battery, other chemistries, which define its density, volumetric, its performance characteristics, and its price. So on the left-hand side, you see different battery compositions. They have various lettering, like NMC is the nickel, manganese, cobalt, and the letters here is the proportion in which all of this mix in. Lithium there is usually everywhere is about 10%. Or 7 here. 7, there's some LFP that have 4, and so on. So this is the chemistry that you have, and they actually have more in development. You can see on the right hand side on the graph there are various other types of batteries, and there are batteries in development. For example, the lithium sulfur, you see this orange space to the right, which has the biggest watt-hour per kilogram output. And so today, for your reference, like your standard commercial NMC battery, NMC cell would have like 250, 240, 260 watt-hours per kilogram. Now, lithium sulfur promises to double that, almost to 500, that's 400 and something. And the thing is that when I was working in a company and we were making a decision to invest, we went for NMC. And lithium sulfur was considered, but we quickly dropped it because it's going to be like commercialized after 2030, no sooner. But actually, a couple of weeks ago, I met a startup which already is raising money for commercial production of lithium sulfur. And they're likely to do that, and they're likely to have that battery operational and manufactured on scale in just a few years. So by 2030, not after that. That's when the lithium sulfurs can be active. And lithium sulfur doesn't require expensive materials and rare like nickel, for example, or cobalt. So this is one way out. You can try to innovate your way out of expensive batteries. Now here you can see the forecasts for the chemistries, the cathodes, anodes to 2030 and forward, and also the casing, your cell format. But here you see that until 2030, nothing really changes much. You have more or less the same chemistries, you have more or less the same electrolyte, you have same anode, casing, whatever. Things start changing on scale after 30s. That's where you have the lithiums. You have sulfur in the cathode, then you have a semi-solids electrolyte, then you have silicon anodes, and all these fancy things which increase the battery density, make it more cheaper, make it more resilient, durable, and so on. So generally, it is viewed by the industry that by 2030s, you would have chemistries and materials which would allow you to sidestep or a little bit at least manage the problem of shortage of materials, of raw materials. So, and that's actually the space where I'm looking at now very attentively, because that's where you can have the innovation, that's where you can have startups making the buck. And that's where you can have startups successful in this industry. There's also another place where you can have a successful startup, but maybe it would take a little bit longer. It's recycling for to also manage the raw material problems that you might have. But here you see the recycling is expected to grow significantly only after 2030. That again is because for the recycling to really hit it off, you need to have a lot of incoming material. It means batteries, which were used up. Now, that's already happening, but in really small amounts. You don't have that many EVs on the road. Not as many as we would like to have. Now, as sales of EVs grow, there will be batteries for recycling. I mean, cars will go out, they will malfunction, they will be sold off, they will suffer accidents. So batteries will go for recycling. But for average electric car, it is expected that the battery will last at least 7 years. So it means a car sold in 2023 will be scrapped no sooner than 2030, and maybe even later. So in 2023, not so many cars sold. Okay, a couple of million cars sold, but still, it's not big by industry standards, and not big enough to make recycling a scalable business. That will happen after 2030, when all the cars sold this decade would start to hit the junkyard. That's when you'll be able to take them, and that's when you have the volume. Now, there are already businesses, there are already companies that are making business out of it, and as you can see on the right-hand side, you could actually have a good margin on recycling, especially if the raw materials crunch will hit by that time. So we have to keep a look out on the recycling market, and also what important about recycling. Important thing about recycling, let me just scroll back to one graph here. The important thing about recycling is that it will make the battery electric vehicles even more greener. So it will reduce this dark navy emission, the emissions that are made in the production. So this will go back. Every new battery electric vehicle which uses the recycled materials will actually have that even less. So that's what I see an important way for the battery and for the car industry. So, in the short, this was the overview of the battery market and its main applications, main markets, and possibilities in the future. I would try to keep this up next year, 2024, maybe doing some deep dives in one or another area. But if you would like to have more of this kind of lectures, drop me a line in LinkedIn, Instagram, or Facebook, and I would be happy to make it for you. So thanks a lot for watching. Please share this video with your colleagues and friends,